One of the hardest things about learning to build your own quadcopter is just knowing which equipment is compatible with which other equipment and where all the freaking wires should go. So I am revisiting a series that I did years ago, actually, how to wire up any flight controller. What I want to do is take you through the thought process of starting with a pile of equipment and then figuring out where all the wires should go. That's right. We're not going to be looking at any of the documentation unless we absolutely have to. I want to show you how you can just look at this stuff, understand the assumptions behind it, and then just know where all the wires should go. I'm Joshua Bardwell, and you're going to learn something today. When I first made my How to Wire Any Flight Controller series, I went through it from a kind of academic approach. We started with power, and then we talked about receivers, and then we talked about cameras, and we talked about all the different permutations of how those things might be wired up. But I want to go about it a little bit differently today. I just want to take a whole bunch of different representative sets of gear, as if we were about to build a quadcopter and you had picked this gear, and then tell you how to figure out how to wire it up. And don't worry, I've picked the gear to try and demonstrate certain concepts, but I want to just build wiring diagrams with you this time, as opposed to breaking it down kind of academically. I don't know, that's just where my head's at right now. Here's the gear that we're going to be using in our first example. I've picked an iFlight F7 flight controller with corresponding ESC, Unified Pro HV video transmitter, Runcam Phoenix camera. We're going to put a Hellgate buzzer on this one. And then as far as receivers go, I've actually put 4 different receivers here, and I'm going to show how to wire them all up because that's a place where there's going to be most diversity and most complexity, actually. Now, the first question that I want to ask whenever I start thinking about wiring up a quad is, does it use individual ESCs or does it use a 4-in-1 ESC? And that's going to be your decision. Some pilots prefer one, some pilots prefer others. If you use individual ESCs, you're going to want an all-in-one or AIO flight controller. An all-in-one flight controller is going to be designed so that the ESCs will solder directly to the flight controller. If you go back far enough, we used to have a whole separate board that we soldered the ESCs to. It was called a PDB. And then once upon a time, somebody decided it would be clever to just make the PDB part of the flight controller itself and save you the trouble. And that's where an all-in-one flight controller came from. If you've ever wondered why are all-in-one flight controllers called that when they don't include a receiver, they don't include a video transmitter, well, it's because back in the day, it was pretty revolutionary. Though, we're going to get rid of the PDB and we don't need that anymore. But nowadays, it's kind of silly to call them all-in-one. Now, in this case, we have a 4-in-1 ESC. And a 4-in-1 ESC is going to be, it doesn't need a flight controller with a PDB built in. It doesn't need an all-in-one flight controller because the ESC itself has, it's all the circuitry, the ESC ought to be called an all-in-one, but it's called a 4-in-1. So this is a 4-in-1 ESC. And it's going to connect to a flight controller that is not an all-in-one flight controller. It's just a standard flight controller. And now in this case, the flight controller and the ESC that we've picked are designed to work together. And so connecting them up will be pretty simple. But we should still look at the pinout for the plug that connects them because we can learn things about the function of the ESC and the flight controller by doing that. And learning those things will help if you ever are in a situation where your ESC is not designed to work with your flight controller. If you're mixing and matching for some reason, then you're going to need to know this stuff. Right here on the underside of the flight controller is the ESC 4-in-1 plug. And you can tell it's the 4-in-1 plug because it has the motor outputs. You see they're labeled M1, 2, 3, 4, and there are a few other things in that plug. The 4-in-1 plug is going to get connected directly to the corresponding 4-in-1 plug on the ESC. And if you are using an iFlight ESC and an iFlight flight controller, you could probably assume that they're just compatible and you just boop, boop, plug them together and nothing will go wrong. And in fact, you can see that iFlight doesn't even print the pinout for this plug on their ESC, which is actually I'm a little annoyed about that. But it's just assumed that, well, it's the same as over here on the flight controller and everything will be fine. Well, what if you wanted to use an iFlight ESC with a non-iFlight flight controller? You would need to know that information. Moving on. Looking here at the pinout of the flight controller, we've got the motor outputs, motors 1, 2, 3, and 4, and that's pretty self-explanatory. That's going to carry the motor signal that makes the motor spin and the quadcopter fly. We've also got ground, and of course you're always going to need a ground reference going between different electronics. And then we've got BAT, which is battery voltage. So one of the things you're going to think about as you're looking at all electronics is how is it getting powered? Every piece of electronics is going to have a certain input voltage that it is designed to accept, an input voltage range, actually. So, for example, for a flight controller like this, the input voltage range might be 7 volts to 30 volts. Okay. Typically, with quadcopter parts, they'll label them as 2S to 6S voltage, and that's telling you what battery voltage it's safe to use with these parts. So this stuff is rated for 6S voltage, and we can see, I'm just telling you that. You can get that from the specs page for the flight controller if you need to go look it up. But it takes battery voltage directly as its input voltage. So the flight controller is going to be powered directly by battery voltage coming in through the 4-in-1 plug. And that is basically always going to be the case for flight controllers that are designed to work with 4-in-1 ESCs, for non-AIO flight controllers. They're almost always designed to take battery voltage, but not always. There are some exceptions. Now, what else is in this plug? Here we've got the CUR, or current sense input. The current sense input is going to it lets the ESC tell the flight controller how much current the motors are pulling. And that's kind of a big deal, because if you don't know how much current they're pulling, you may not care if your motors pull 20 amps or 30 amps or 100 amps. Really, who cares? Unless you're doing some kind of, a lot of people don't care. But a lot of people do care about the milliamp hours. The milliamp hours is like your quadcopter's gas tank. Milliamp hours. Voltage also tells you when your battery's dead, but a lot of people prefer milliamp hours to voltage. And without knowing milliamp hours, without current, you can't know milliamp hours. So this ESC is doing analog current sense input, and that's compatible with between the ESC and the flight controller. The other kind of thing that might be coming from the ESC is Esc Telemetry, and oh, how about that? This ESC also is doing telemetry. Isn't that nice? Almost as if I did that on purpose, but I didn't. The other pin we see here is R5. And whenever we see like T5, R5, or something like TX5, RX5, what that's referring to is a UART, a UART, a Universal Asynchronous Receiver I don't know. I'd have to go look it up. A UART, think of a UART kind of like a USB plug on your computer. You plug peripherals into a UART, and they're used for communication. And the UARTs on your flight controller are numbered and used to talk to, well, we'll see the kind of things they're used to talk to throughout this example. In this case, the ESC has a function called Esc Telemetry. Esc Telemetry. And Esc Telemetry comes into the flight controller through a UART. In this case, it's going to be R5. So when you look at a 4-in-1 plug and you see R5 or R6, that's telling you that that is an input for Esc Telemetry. When you look at an ESC plug and you see CUR, or current, or C, that's telling you that's an input for analog current sense. With analog current sense, the value is represented as a varying voltage level from 0 to 3.3 volts. The more voltage, the more current, and that's translated by the flight controller into a certain number of amps that the ESC is telling it that it's pulling. So this flight controller actually supports both analog current sense input and Esc Telemetry, and I think we can assume that the ESC is also going to send that information, although some flight controllers will have both of those pins just to give you the flexibility to choose which one you want to use. Not all ESCs will support both of those functions. So that sorts out, well, it sorts out our motor signal wire connections. It sorts out our question of how are we going to power the flight controller. And frankly, anytime you've got a flight controller and an ESC together, they're just going to plug together, and those questions are probably going to have been solved for you by the manufacturer. So it's very nice. A lot of people prefer 4-in-1 ESCs because they're so much easier and quicker to wire up than having to figure all this stuff out yourself. Now things get a little more complicated. Let's start with the video transmitter, okay? And as with any electrical device, the first question we got to ask is, how are we going to power it? And the first thing we need to know is, what is its rated input voltage range? And here, TBS has made this very easy for us. This is I screenshotted this from the documentation. It is 7 to 26 volts in. So we need a minimum of 7 and a maximum of 26 volts. And if you think about it, that corresponds to 2S roughly voltage all the way up to 6S voltage. It's very common these days to find electronic devices taking up to 26. Shit. Stop. Stop. There's a leak. It's very common these days to find electronics for quads rated up to about 26 volts or maybe a little higher, because that corresponds to the voltage of a 6S battery, and people are very commonly running 6S batteries these days. So we're going to need ground, and we're going to need a source of between 7 and 26 volts. And the simplest way to do that is to connect it to battery voltage, or VBAT as it's commonly written. So let's look at our flight controller and see what our options are for powering the video transmitter. And as you do that, you want to try to get into the head of the designer of the flight controller, because chances are they didn't just put all the pads and they just didn't put everything willy-nilly. They put it in a way that sort of makes sense and suggests how you might be intended to use it, although of course you can do whatever works. These pads here are labeled M1, 2, 3, 4, 5, 6, 7, 8. These are the motor outputs, and we already saw the motor outputs down here in the 4-in-1 plug. We have motors 1 through 4 going direct to the ESC. These pads have been placed here in case you want to direct solder the wires instead of using the plug, and we've actually got up to 8 motor outputs if you wanted to have like a hexacopter or an octocopter, or if you just lifted one of the pads and needed a spare motor output. So these are the motor outputs, and then next to that we've got current sense, R5, or is that R6? I can't quite read it, and VBAT and ground. So conceptually, this group of pads is essentially duplicating the function of the 4-in-1 plug. It is the sort of, we're thinking about the ESC and the motors as we look at this group of pads. Well, that doesn't have anything to do with the video transmitter. If we continue over this direction, though, we find things a lot more sort of relevant. We've got a camera output here, or input. Well, we'll have to think about that. We've got a camera pad. It's labeled CAM. And we've got VI and VO. Okay, so VI and VO stand for video in and video out. Video in is going to come from the camera, video in from the camera to the flight controller. VO is video out. It's going to go out from the flight controller to the video transmitter. If you think about it, it sort of makes sense. The camera creates a picture. It sends it into the flight controller. The flight controller puts the OSD, the on-screen display, it puts all that information on the camera feed, and then sends it out to the video transmitter. Sometimes you'll see these pads labeled CAM or CAM_S for camera signal. Sometimes you'll see the video transmitter pad labeled VO, or sometimes it's labeled VTX, or occasionally you'll see VID. If you're ever not sure, you can always look up the documentation, but a lot of times the terminology is going to be standardized here. So we've got VI and VO, and those are for the camera, the video transmitter, so we're clearly sort of in the right neighborhood here. What else is nearby? There's a 5-volt pad, a BAT pad, and BAT or VBAT are basically the same thing. And then we got some ground pads. So we have our choice. And by the way, we could power the video transmitter from any one of these pads that was outputting the right voltage. But in order to keep the wiring sort of neat and tidy, it would make sense to do it from here. And which one of these pads are we going to choose? Well, we need between 7 and 26 volts to power our video transmitter. We have the choice here of 5 volts or BAT, and that BAT is clearly the one that we're going to pick. We're going to take here, and we're going to go from this wire, 7 to 26 volts in, and we're going to go to the battery pad, 7 to 26 volts in. And here is ground, and we'll just take our black ground wire over here to ground. All right. Now, video transmitter outputs video, and that is going to be on the video wire. So typically that wire is going to be yellow, although not always, but we'll use yellow here. And we'll go from VO, video out, to video. All right. Well, we've got the most basic functions for our video transmitter here. There are a few more things that we might hook up. We'll get to those in a minute, but let's move on and do our camera next. And again, the first question we're going to ask is, what's the rated input voltage range for this device, and how can we give it the voltage that it wants? Now, this camera is rated for 5 to 36 volts, and this is interesting because it means we have the choice of using either VBAT or 5 volts. And you could certainly ask a question, well, which of those should I pick? Certainly one way to go about it is to say, my 5-volt pad is not used yet. It's convenient to solder one wire to each pad because it means that if you ever have to redo the work or anything, it's a little simpler because you just desolder one wire and then solder something else back down. You certainly could connect the camera to this VBAT pad. What you would want to do then is you would just strip the wires, twist them together so they're twisted together, tin them so that they're soldered together to each other, and then solder them both down to the same pad. There's nothing wrong with doing that. As far as the input voltage goes, sometimes you'll get a cleaner image by feeding the camera a filtered 5-volt input as opposed to giving it battery voltage. Battery voltage is not being filtered at all, and so any electrical noise that comes from the ESCs will affect your image quality somewhat. So a lot of people would choose to run the camera off of 5 volts if they had the option, and we do. You certainly could choose. The flip side is, if the 5-volt regulator is just kind of crappy, the 5-volt regulator itself can inject a lot of noise and make your video worse. So it's kind of a toss-up. In this case, I'd probably solder it to 5 volts because the 5-volt pad is free and it keeps my wiring cleaner. But if I had messy video, I would consider moving it over to VBAT. So we're going to go from 5 volts here all the way over to our 5-volt wire. From ground all the way over to ground. Oh, I've kind of left myself not a lot of room. And then the video wire from the camera is going to go to, let's just, we need to go from here. So to the VI pad, video in from the camera. We're going to come all the way over here and go to video. Wonderful. Where do we go from here? Next, let's talk about smart audio. The first thing I want to tell you about smart audio is it has nothing to do with audio. If you want to use like an earbud like Mr. Steele does to hear your quadcopter motors while you fly, that has no relationship to smart audio. Smart audio has the word audio in its name because of a quirk of how it was developed. But what it actually does is it lets you configure your video transmitter power and channel without ever touching your video transmitter. Way back in the day, video transmitters had dip switches, and you had to flip the dip switches to change the channel, and it was a pain in the ass because, number one, knowing what the dip switch is, you had to carry a little sheet in your pocket, which was the dip switches, so you knew which channel you were on. And then number two, you had to get at the video transmitter, and it's like, oh, what a hassle. Smart audio lets your flight controller communicate to the video transmitter and say, what channel are you on? What's your output power right now? And you can see that information in your goggles. And then you could say, oh no, I want you on you just use your transmitter sticks to change it around. So you want smart audio. You definitely want it. And the way it's going to get hooked up is like this. Smart audio needs to connect to a UART TX pad. A UART TX, a UART transmit pad. And so let's look. What options do we have? Well, very conveniently right down here, in the same neighborhood as all the other settings, is this T2 pad. T2 or TX2 is UART2TX. Now, before you go assigning and mentally mapping out your UARTs, you need to know that you can only use each UART for one function at a time. So if somewhere else in the wiring diagram you had used R2 for something or T2 for something, you couldn't use it here as well. In fact, if you solder two things to the same UART pad, they can conflict and neither of them will work. Nothing will be damaged, it just won't work. But in this case, we haven't. So let's see, what have we used? Well, actually, we have used one UART so far. I believe it's, hang on. Yeah, it's 5. So we got R5 down here. So UART 5 is taken. And then UART 2 is free. So that's the one we'll use. Great. Orange wire here. And we'll go all the way around to smart audio. Perfect. Now you may have noticed that this video transmitter is actually labeled both Crossfire and Smart Audio. And that is something that TBS video transmitters can do. TBS video transmitters can connect directly to a TBS Crossfire receiver. This is mostly used in a case where you didn't have a flight controller, like if you had a fixed wing and it didn't have a flight controller, you could connect the video transmitter directly to the receiver and they could talk. But most of the time when you're working with a Betaflight flight controller, you're going to be using smart audio. So we're going to be using this Crossfire wire, but this TX1 wire we're simply not going to be using. So we'll just X that out. And as long as we're Xing things out, we've also got a ground and a 5-volt output from the video transmitter. And the purpose for that, again, is if you were putting this video transmitter in a plane or something that didn't have a flight controller, that 5-volt output could be used to power the camera. And sometimes people still do that on quadcopters, because sometimes, like I said, maybe the 5-volt regulator on this flight controller is crappy, and you're getting a whole bunch of video noise. And you're like, well, let's try something else. Well, a workaround for that could be to connect the camera to this 5-volt out from it's just another regulator. Let's try something else. But in this case, we're not doing that. And again, we're just going to X these out and we're not going to use them. So that's it. We've completely wired up our video transmitter. Fantastic. Well, as long as we're completely wiring things, let's finish wiring up the camera. And you may be saying to yourself, what do you mean we've wired up the camera? What's left? Well, there's the joystick plug for the menu. Does this one have it? Yeah. And in case it's not like obvious, that's intended for like this kind of joystick, right? That you plug into the back of the camera and you configure the camera. But that can actually, many modern flight controllers actually have the ability to interface with that. If we look up here, we've got this cam pad. What is that? You'd think it was for the camera, but we've hooked the camera to VI. Well, the cam pad is used for a function in Betaflight called camera control, where the Betaflight flight controller can connect to the joystick and kind of emulate the joystick. And so what you would do if you wanted to take advantage of that is you're going to take this cam pad and you're going to solder it to, I'm really running out of room here. You're going to take this cam pad and we're going to solder it to the menu pin or the menu wire. Let's just do this. Let's just go like this. Uh-oh. Oh no, this marker is... So we'll take menu over here to... This green is so dark it kind of looks black. Over here to cam. Okay. Now I should tell you that if you try and hook up this function and use it, it often just doesn't work. And there are some command line parameters you can play with to try and make it work. But the bottom line is it's a very difficult thing. And it's kind of cool that some flight controller designer and Betaflight dev were like, let's try and do this. But when it works, it's great. And if it doesn't work, you could just be out of luck. There is an alternative called digital camera control that we're going to look at in a future example. And we'll see a better choice. It's worth trying to hook it up. If your flight controller has it, you may as well try to hook it up and just see if it works. Well, now we come to receivers. And receivers are, I kid you not, getting your receiver hooked up is the single most difficult thing that I think most beginners run into. If I had to pick one question that I get more than any other, it would be people who can't get their receiver to work. So I'm going to show you a bunch of different examples of how to hook up a receiver, and hopefully it'll start to make some sense. Now, the first thing I want to tell you is that we have intentionally picked an F7 flight controller. What that means is that this chip here, it's actually upside down, but you can see it's labeled STM32 F722, F7. And the reason I did that is because F7 flight controllers support a function called UART inversion. You don't need to memorize that, but suffice it to say, it means it's a lot simpler to hook up your receivers. And specifically, if you have FreeSky receivers, if you have Crossfire, FlySky, Spectrum receiver, everything I'm going to say is the same, whether you've got an F7 or whether you've got an F4. F4 is the other kind of processor. So this is an F7. The alternative is an F4. Before F4s, there was F3 and F1. What happened to F2 and F5? I don't know. Forget about those. F1s and F3s are basically obsolete today. All you guys who are still flying F3s, tell me in the comments they're not obsolete. But basically, all flight controllers sold today are F4 or F7 or better. Okay, so we're going to start with the non-FreeSky ones because that's actually going to be the same no matter what you've got. And we'll start with this guy, which is a Spectrum receiver. And as always, we've got to ask ourselves, what is the input voltage that this can take? And how are we going to give it the input voltage that it wants? Now, older Spectrum receivers, Spectrum satellite receivers especially, could only take 3.3 volt input. Most receivers take 5 volt input. So you're definitely going to want to check whether your Spectrum receiver is rated for 3.3 or 5 volts. If you give it 5 volts and it's rated for 3.3, you can fry it. The next thing let's do is let's look around our flight controller and sort of try to find the neighborhood where the receivery things have been placed by the board designer. So we had the motors and the ESCs. Here's the video and the camera. And if we come over here, let's see, we've got the buzzer and the LED. And then over here, this is the sort of receivery area. And we can tell that most significantly because here's a 3.3 volt pad. 3v3 is what it's labeled. And almost always when you've got a 3.3 volt output on a flight controller, that's intended for Spectrum satellite receivers. But mostly what we're looking for is there's kind of going to be, on an F7, there's going to be sort of a block of UARTs all together. And that's where the receiver is going to go, as well as any other peripherals that you might have using those UARTs. So here we've got R6, R4, R3, R1, and T1, 3, 4, 5, 6, right? Those are our UART TX and RX pads. Now this receiver that we're using is the Spectrum 4650, and it is one of the newest Spectrum receivers, and it takes a wide voltage input range between 3.3 volt and I think 8.4 volts. So we could power it off of 3.3 volts if we wanted to. We could also power it off of 5 volts. There's really no advantage to doing it either way. Some flight controllers are not going to have a 3.3 volt output, and in that case, that's why they want it to have a wide voltage input range. But what the heck? Let's go ahead and power this off of the 3.3 volt input because, well, we can, so why don't we? Let's come around here. 3.3 volts to all the way down to the plus. That's going to be our power. And of course we need ground, and it's just convention that here's a 3.3 volt, boop, here's the corresponding ground. You could use any ground pad, but keeping the wires together kind of keeps everything neat and makes it make sense. And we'll take ground and we'll come around. And we'll go to the minus pad. Now the next pad on this receiver is labeled NC, and NC stands for not connected or no connection. When you see a pad or pin labeled NC, it just means it doesn't do anything. Just forget it. It doesn't do anything. And then finally, we have to figure out where to connect our signal wire from the receiver. Now, receivers, you used to be able to say that a receiver signal wire would always go to a UART RX pad, a UART receive pad. But that's not actually 100% true anymore. And this Spectrum receiver is an example of that exception. If you have a Spectrum receiver, you can connect it to a UART RX pad like R2, but the newer receivers that support telemetry, like the 4650, that support the SRXL and SRXL2 protocol, they are actually going to go to a UART TX pad. Now, you may think T2, well, it's right here. It's an obvious choice. It's in the neighborhood. But remember, we already used T2 over here. So we can't use it again over on the other side of the board. We need to not use T2. And correspondingly, we cannot use R2 Once UART2 is assigned to something, it can't be used for anything else. So we're going to cross that off. Well, then okay, fine. I'll just use T5. No problem. Doesn't really matter as long as it's on. Oh, wait a minute. Oh, we used R5 down here. We used R5 for Esc Telemetry down in the 4-in-1 plug. Aha. Okay, no problem. T5. That's off the table. And R5 is off the table. Okay, well, that's fine. We're still good. We got a lot of UARTs left. Let's just use T4. Have we used T4 anywhere else? No, we haven't. So we can use T4 for that signal wire if we so desire. We're going to use T4 because this is a newer SRXL spectrum receiver, and they use the TX pads to the signal. Now at this point, things are going to get very messy if I keep drawing on the diagram, so I've printed a fresh, clean one, so that's where all the wires went. Let's do the next receiver, and this is a FlySky Flea 14 Plus receiver. It is going to output the iBus protocol. It's an iBus receiver. Spectrum is SRXL, SRXL2, or Spectrum protocol for the older ones. This is going to be outputting iBus, and the first question we got to ask is, where's it going to get power from? And it is, except for Spectrum receivers, it's basically always safe to assume that receivers will take 5-volt input. Sometimes they can take up to like 8 or 10 volts, and in theory you could power them off a 2S battery if you ever needed to, but I don't know why you would. But it's basically always safe to assume a receiver will take 5-volt input. So in this case, I've had to blow this up a little bit because it's not very legible, but it's labeled ground, GND, VCC, and iBus. And this is a little confusing because VCC in electronics circuitry basically just means supply voltage, but it's oftentimes used as an equivalent of battery voltage. Sometimes you'll see VBAT labeled as VCC. VCC refers to any supply voltage. It's no particular voltage. So it's not incorrect of FlySky to put, or who makes the Flea Plus? It may not be a Fly, maybe a third party, I don't know. It's not incorrect to label this as VCC, but it is a little confusing because you might think, oh, that's VBAT, and give it 16 volts and fry it. It probably can't take 16 volts. We're going to give this 5 volts as its VCC input. And conveniently, over here in the neighborhood, here's a 5-volt and a ground pad. So let's go ahead and ground. And then lastly, signal. And where are we going to put signal? For iBus receivers, the signal goes to a UART RX pad. So we have the same situation that we had before. We can't use R2 or T2. They're already used. We can't use R5 and T5. They're already used. So we're going to use R4. To the iBus. Simple. Very simple. Now Crossfire is a little different than the receivers we've seen so far because Crossfire supports telemetry. Well, the Spectrum receiver also supports telemetry, but the Spectrum receiver does telemetry over one wire. There was only one signal wire on that SPM 4650 receiver, and that wire is going to send the control data one way and the telemetry data the other way, and they're just going to kind of take turns going one way the other way. But Crossfire does it with 2 different pins, and the way that Crossfire receivers work is channel out number 1 is the TX, and channel out number 2 is the RX. And this is just going to hook up to our UART. Now there's something you need to know about UARTs. Almost always the standard is that TX on the one device goes to RX on the other device. They basically flip in the middle. And that's a little confusing because normally if you have a 5-volt pad on your receiver, you connect it to a 5-volt pad. The labels are the same on either side, and that's how you know they match up. But UARTs don't work that way. So we've got 5-volt and ground, and so I'm going to spare you. I think you can figure out how to do 5-volt and ground at this point. You've seen enough examples. But with the TX and RX, we're going to take TX from the receiver, and we're going to go to RX. Let's just use R3 here. R3. RX on the flight controller. And we're going to take RX on the receiver. Yeah, that's better. It's a better color green. And we're going to go to TX on the flight controller. And for the sake of this diagram, I have I've shown both the FlySky and the Crossfire receiver hooked to different UARTs. You would not hook two receivers up to the same flight controller. That's just me saving a piece of paper that I would have to print. So that's how the Crossfire would hook up. Finally, we come to the FreeSky receiver, and here's the quirk with FreeSky. FreeSky outputs S-Bus as its control protocol and SmartPort as its telemetry protocol. And both of those have a characteristic called inversion. They are inverted serial protocols. It just goes back to when FreeSky defined them, that's how they defined them. And nobody else does this. No other receiver protocols, there's no other example of inverted protocols that I can think of in all of RC. And it doesn't matter if you're using an F7 processor on your flight controller, because F7 processors can handle inverted serial signals, but F4 processors can't. And the designer of an F4 flight controller has to take that into consideration. We'll see that when we get to an example with an F4, but let's do the F7 example. It's actually not too bad. First question we ask is, how do we get power? And you can see it's labeled 5 volt and ground. So we'll give it 5 volts. 5 volts. And ground. Sure, no problem. Great. So then the next thing that's a little confusing about this particular receiver, the FreeSky RXSR, is that it has an S-Bus in pin. And that's used for if you had two receivers on the quad at once, one receiver could feed into the other one, and then you would have redundancy. If one receiver failed or lost, I don't know. But most people doing multi-rotors don't do that. And so generally, you're simply going to ignore the S-Bus in pin. Then we've got SmartPort, and SmartPort is going to be the yellow wire coming out of the header. And SmartPort is going to go to a UART TX pad. So for example, we could go to T4. And then we've got S-Bus out, and that's going to go to a UART RX pad. So, and you might think we could use R4, but remember, once you've used a UART for one function, you can't then use it for a different function. So since we use T4 for SmartPort, we have to use a different UART. We'll use R3 for S-Bus, and that's how we would wire that up. Finally, we come to the Hellgate buzzer, and I'm kind of wishing I hadn't put the Hellgate so far from the buzzer pads, which are up in this corner. But the wiring up the Hellgate is pretty simple. We need ground, 5 volts, and buzzer minus. And we're going to find those here. We've got ground. Here is buzzer minus. And notice that this pad is labeled 5 volts and buzzer plus at the same time. On almost every, pretty much every, I kind of hesitate to say every because somewhere out there's an exception, but on basically every flight controller, buzzer plus is just 5 volts. So that's how you would wire that up. Buzzer minus, 5 volts and ground. I'm not going to draw the wires all the way across the, but you see what we got there. And that's it. Now you have your wiring diagram for your quadcopter. You're ready to start soldering it up. And whether you draw that out on paper before you start, or whether you just kind of feel it out as you go, that is the thought process that I would use if you just handed me a pile of stuff and then asked me to wire it up. Of course, once you get it all wired up, then you have to go into Betaflight and configure it, and that, of course, that's going to be a topic for another video. I know this video has gone on for a little while, but I want to do a couple more examples so the information is all in one place. And if you need to pause the video and come back, that's great, but I'm going to keep going with a second example. And the first thing I want you to see is that this ESC has these great big ESC plus and ESC minus pads. That is how you know it's an all-in-one ESC, and it's designed for use with individual ESCs. Of course, it does have a 4-in-1 plug on the other side. You can use it with a 4-in-1 ESC, and in fact, I have my own JB ESC that goes with it. But if you want to use a 4-in-1 ESC, then you get a lot, like compare the JB to the iFlight, right? Look at all the pads the iFlight has. Generally, a non-AIO flight controller is going to have more functionality and more flexibility because the board designer can just put everything in the kitchen sink on the board. They don't run out of space. Whereas on the JB, or on any all-in-one, so much space on the board is taken up by these pads that oftentimes the board designer has to make some compromises and leave some functionality out. So, where are we going to hook this up? Well, we're going to start with the ESCs. So the ESC is labeled plus, T, S, and minus. And plus and minus are assumed to go to the ESC plus and minus pads on your flight controller if you have an AIO flight controller, or on your PDB if it's 2014. So we're going to hook plus here, plus to plus, and minus to minus. And you can see the flight controller has different plus and minus on each corner. Minus and plus. There's one on each corner. Minus. And we'll do this one too. ESC minus and plus. Plus. Okay. So now our ESCs have power hooked up. You may be tempted, if, for example, you were to lift one of these pads, you may be tempted to, well, I'll just solder this black wire over here. And you don't want to run two ESCs off of one pad. Electrically, it does work, but the problem is that you may pull more current than the pad is rated for because you're running two ESCs off of it. So the voltage would be correct, but the current may be too high and you may burn out the pad. The next wire I want to look at is the S, or signal wire, and that is going to go to the motor outputs on the flight controller. And in this case, the flight controller has signal wires here in the corners. If we compare that to the iFlight, it had the motor wires here in a row, the motor outputs. But because the JB flight controller is an AIO and is designed to be used with individual ESCs, we put the signal outputs in the corners so the wires stay short and neat. Now these pads are teeny. Look at these little teeny pads. Another reason why 4-in-1 ESCs are good for beginners is because they save you some of this soldering where you may damage something. Yeah. So here is the signal pad rather, and that is going to go to S4. And then we have T for telemetry, which is for ESC telemetry. If you want to use that, that's not mandatory, but you will go to the RX4 pad on the flight controller. And again, we put RX4 here specifically for that purpose. It's worth pointing out that the main piece of information that ESC telemetry sometimes carries is current information. So you can get that milliamp hours gas tank for your quad and know when your battery is about to be empty. The other information carried by ESC telemetry is the temperature of the ESC, if it's getting hot, and the motor RPM. And frankly, that information is not that interesting. I mean, motor RPM is interesting, but you can do it these days with bidirectional D-shot instead of ESC telemetry. So honestly, on most of my builds, I would leave the RX4 wire off. I just would save myself the solder points and not do it. But you may say, well, what about that milliamp hours? What about that gas tank? Don't I want amps and milliamp hours? Yes, you do. But on an all-in-one flight controller, the flight controller, the XT60, it's on the underside, so you can't see it in this picture. The XT60 is going to solder to the flight controller itself. And the flight controller is going to have a current sensor built in, and it will already know the milliamp hours and the amps, even if you don't use ESC telemetry. So with individual ESCs, you generally do not need ESC telemetry to get the amps and milliamp hours, and the other data it gives, RPM and temperature, I don't usually care enough about to solder up the telemetry wire. So enough about that. Next, let's do the video transmitter. And the video transmitter I've picked here is the Rush Tiny Tank. And the reason I've picked it is, well, let's ask the question, how are we going to give it power? And you can see that it is labeled plus 5 volts. Most video transmitters these days are rated for VBAT input and can take battery voltage. But the very smallest ones are usually rated for 5 volts only. And the reason for that is that when you have VBAT coming in, then the video transmitter itself has to have a voltage regulator on board to take that battery voltage and step it down to 5 volts or 3.3 volts, whatever the video transmitter uses internally. By leaving that voltage regulator off, the video transmitter can be made much smaller, but the flip side is that you can only give it 5 volts. You can't give it like 7 to 26 volts. So we got to give this guy 5 volts. And let's look at our options. Well, first of all, let's just look at the flight controller and see where in the neighborhood did the flight controller designer expect you to be thinking about the video transmitter. And this one's a little different because on the iFlight, the camera and the video transmitter were kind of in the same neighborhood as each other. But in this case, what I was involved in designing this board, so I can tell you what I was thinking. We've got the camera and the receiver coming off the front of the board, and we've got the video transmitter coming off the back of the board, because the camera is usually going to be at the front and the video transmitter is at the back. So this has fewer wires crossing over the flight controller. So in this case, we've got video, 9 volt, ground, TX4, RX4, and then up here we've got LED, ground, VCC, it's a little hard to see, that's labeled VCC, and buzzer, plus and minus. So we need 5 volts. Wow. So this flight controller actually looks like it was designed more for video transmitters that take VBAT. But there's a secret here. Because the buzzer plus pad is also a 5 volt output. So what we can do is this. From buzzer plus, we're going to go to 5 volts. Here we've got ground. Going to ground. Wow. We've got a cam. That's interesting. That's unfortunately labeled. Let's come back to that. Here we've got VTX. That's got to be the video output. What else could it possibly mean? One of these has to be the video output. That's probably it. I might confirm that in the manual. On the JB flight controller, the video pad is for the video transmitter. Cam 5 volt ground. Yeah, look over here. There's cam 5 volt ground. All right, so this has to be intended for if you wanted to solder a camera directly to the VTX. Yeah, that's got to be what it's for. If you didn't have a flight controller and you wanted to solder a camera directly to VTX, this would just sort of pass through 5 volts to the camera. So we're not going to be using this at all. And then here we've got the cam pin. Is that the same thing? I would have to look that up. This is a little bit of an unusual labeling. I would have to look that up. Why would you have cam over here and over here? It seems a little strange to have the same pin in 2 different places. Well, we've got video, power, and ground. The other thing we're going to get is the smart audio, the remote control, and that is going to be the data pin. So sometimes that's labeled SA, sometimes it's labeled TX or RX, and sometimes it's labeled data. It's sometimes labeled different things, but you know that one of these pins is going to be smart audio, and in this case, well, what's SW? I'm guessing that stands for switch, and maybe you could hook this up to like a receiver and switch it. We'd have to read the manual to figure out what the cam and the SW pads are for. I'm not actually sure off the top of my head. I could guess, but I'm pretty confident that the data wire is for smart audio, and that's going to go to a UART TX pad, and that's how we would wire that up. I've made a mistake. I accidentally put I put the rush tank on TX4, but I also put Esc Telemetry on RX4. Like I told you, I never do Esc Telemetry, so yeah, it doesn't matter. I wouldn't do that anyway. I would use smart audio. Next, let's do the receiver. And the receiver, so we've got 5 volts in ground, and we're going to need to find those. And that is going to be on the JB flight controller. There's something novel here. Notice that this pad is labeled 3.3/5. Remember I said that older Spectrum receivers used 3.3 volt input, but most other receivers used 5 volt. Well, unlike the iFlight, which had a separate 3.3 and 5 volt pad, there's not enough room for that on the JB flight controller because it's an all-in-one. We ran out of room. So there's a single pad that outputs either 3.3 or 5 volts. Well, how do you tell? And the way that you tell is on the underside of the board, there is a solder bridge here. This is on the underside of the board, and what you would do is you would take a soldering iron and you would make a blob of solder between these two pads so it connects them. And that's how you choose 5 volts output for your receiver, or 3.3 volts if you prefer. But the RXSR takes 5 volts, so we're going to wire it to 5 volts and ground. And in order to keep the picture neat, I'm not going to draw the red and the black wires. Then we've got SBus out, and that's going to go to, SBus goes to a UART RX pad, a UART receive pad. But on an F4 flight controller, that's not going to work because SBus is an inverted protocol and F4 processors can't handle inverted protocols. Instead, what you're going to see on F4 flight controllers is the designer will give you an SBus pad. And the SBus pad has an inverter on it to uninvert the inverted SBus protocol so the F4 can handle it. And so here we've got the S for SBus pad, and that is going to go to SBus out /CPPM. Now, the question that you then have to answer is, what UART number does that correspond to? Because it's going to be connected to some UART, and you got to look in the user manual to find that out. It's not always obvious, and that's one of the things that's annoying about FrSky receivers. Sometimes right next to the SBus pad will be RX1, like the Emacs Magnum flight controller does this. There's the SBus pad, and then right underneath it, there's R1. And you're like, well, chances are SBus is UART1. But in this case, you just don't know. There's just no indication here of which UART this is. So you would have to look in the manual to find out that SBus is UART1. Smart port telemetry is also inverted. Normally it goes to a UART TX pad, but on an F4 processor that doesn't work. You have to have a special T for telemetry, or sometimes it's labeled S-port pad that the designer has given you. So that's how that's going to go. And again, you need to find out by looking in the documentation for the flight controller which UART that T pad goes to, so that when you're setting up Betaflight, you can configure it on the right one. Many flight controllers by default will have serial receiver enabled on the correct UART for the SBus pad and smart port telemetry already enabled on the correct UART for the telemetry pad. So sometimes you just plug into the computer, you connect to Betaflight, and you look in the ports tab and it's already there for you. But a lot of times it's not, it's just blank, and you got to know by consulting the documentation for the board, which is sometimes a pain in the ass to find, and you can't find it, and you're asking around and you don't know. And that's one of the reasons why F7 processors are simpler when you're dealing with FrSky receivers. Now, lastly, we come to the camera, and I picked this camera. This is the Runcam Racer 3, and I picked it because it has a feature that I want to focus on. So connecting up the camera is going to be no different than we saw before. We've got 5 volts, video, and ground, and they would go to where? Well, where would they go? Here on the JB flight controller, it's a little difficult to read because I drew over it, but there is cam_C and cam_S. Cam-C is analog camera control. That thing I told you about before where you hook it up where the joystick would hook up, it would be this, the M pin. Why do they call it M? What is that? Menu. It must stand for menu. Okay, fine. Cam-C, that's this pad here that's been colored over by the green marker. Cam-C would be the camera control. But, like I said, that often doesn't work. Runcam cameras specifically have a thing called digital camera control. And the way that works is you hook the camera up to one of the unused UARTs and they talk digitally and it just works and it's amazing. And the way you can tell that you've got a camera that supports that is you will see TX and RX on these last 2 pins instead of ground and menu or ground and OSD. Now, in this case, we've got both. We've got ground/TX and menu/RX. And that is because the Runcam Racer 3 can actually do either joystick or digital control. And that's pretty cool because if you have a camera that only does digital control, well, then how do you configure it if you don't have a flight controller? You can't. So on this guy, what we're going to do is we're going to find an unused UART. And in this case, we've got T6 and R6 are not being used. And what we're going to do is we are going to connect TX on the camera to RX on the flight controller and RX on the camera to TX on the flight controller. Remember, TX and RX swap. Well, there you go. That is basically, that's like 95% of what you're going to encounter when you have a pile of stuff and you're trying to figure out how to wire it up. Hopefully at this point, if you really, maybe to watch the video 2 or 3 times before it all sinks in, but you'll actually just be able to sit down and draw your own wiring diagram for how to wire this stuff up. If you have any questions, put them in the comments. If you have a wiring diagram you want me to take a look at and check for you, send it to me on Facebook. Just message me on Facebook Messenger and send me your wiring diagram. I'll be glad to take a look at it. I do my best to answer all the messages that I can. I want to warn you, a lot of times when a video gets past a certain age, YouTube stops showing me notifications for the comments, and then I won't see them, but I would never intentionally ignore you. So just message me or leave a comment below, whichever one works. That's going to do it for this video. I want to take 1 second and let you know, if you did watch this video like 3 times and then it finally all sunk in and you were like, I see the code of the Matrix. I know how to wire up flight controllers. It's so amazing. I have a Patreon. Little as $2 a month or more if you feel like I've earned it. It's a great way to show your thanks, and it means a lot to me if you decide to join up. That's going to do it for this video. Thanks so much for watching. Happy flying.